Hello, everyone. Welcome to this CS201 seminar. So it's my pleasure to introduce Siddharth Srivastava. So he's currently an assistant professor at Arizona State, previously postdoc at Berkeley, I believe with Stuart Russell, PhD from UMass Amherst, right? Got that correct. So he works on planning, reasoning under uncertainty, and how to act in the world that is uncertain. And he's one of the big shots in the ICAPS community, which, as you may know, is kind of the area of within AI where people study planning, and witnessed by a Best Paper Award from ICAPS and being former conference chair of ICAPS. And so he's here to tell us about the latest developments in the planning community within AI. So Sid, the floor is yours.
Thank you, Geet. Thank you for that kind introduction, and thank you everyone for coming. I know Zoom fatigue is a real thing, so I really appreciate it. And in the interest of keeping things lively and interactive, I welcome questions at any point during the talk. So please, unmute yourselves or find a way to speak up, and I'll be happy to take questions during the middle. So I'm going to be talking about assistive sequential decision making. So the obvious question here that I want to start with is, what is assistive sequential decision making? I'm going to get my phone out of the way because I'm getting lots of scam calls. Anyway, so we don't have a community agreed upon definition for assistive sequential decision making. So what I'm going to do instead is show you by example. So this is from an NSF project that we did, and the idea was to design ways in which robots could help humans in agile manufacturing. So in this use case scenario, we have a user who has a design in mind, and they're getting help from the robots in assembling it. So in this case, you can see, every once in a while, the user needs something and the robots get that part for them. And in this example, the fetching or the activity of the robots is relatively short horizon in the sense that it's just picking up an object and giving it. But in general, I'm thinking of problems where the user has an objective in mind and the robot has to somehow figure out what to do in order to achieve it. So they might have to go and search the warehouse for parts that are needed, or even manufacture a small component and bring it. And the user uses this in their way, in what they want to do. So I'll focus on this kind of assistive sequential decision-making and assistive AI. And you can think of these kind of systems intuitively as systems that make it easy for the operators to use, right? In the sense that the operator has a high-level objective and the system figures out how to achieve that and help the user in that task. And I'm calling this a principle rather than a definition because it's not a Boolean condition. You can measure how well a system complies with each of these concepts. For instance, how easy is it to use, who qualifies to be an operator, and what does safety mean for that context. And this principle that I'm calling P1 is an aspirational goal for most of today's AI systems. So it's a good starting point, but it turns out that it has some limitations. And the concerns that we are seeing about AI and future work and AI safety actually stem from the limitations of P1 as a principle for designing AI systems. For instance, you could have an AI system that is compliant with P1, but it is such that very few people qualify to be its operators. So you have concerns about future of work, as in how expensive is it going to be to train new people to work with this kind of system? Or you could have an extreme form of this where no one is qualified to be a safe operator for this system, for this AI system. It is still P1 compliant, but vacuously so. And so there are all these loopholes because P1 is not really considering the cost or the feasibility of training operators. So I think a better, more general principle for us to think about as we design AI systems is what I call P2, because it's a little better than P1, right? And this principle is saying that an assistive AI system must make it easy for its operators to learn how to use it safely. And naturally, systems that are going to be difficult to use or difficult to control wouldn't qualify or wouldn't comply with the learning aspect or the learnability aspect of P2. So for the past few years, my group has been looking at different aspects of P2 compliant AI systems. And I'm going to focus on some of our recent results along these directions. And in particular, what we found is that state and action abstractions are surprisingly useful in many of these aspects of P2 systems. They help us do data efficient planning and learning so that the user doesn't have to specify lots of detail about how an AI system should operate to help. They can also help users understand what the limits and capabilities of an AI system are, which really helps in safe usage of AI systems. Now, these principles can also be used to provide explanations of AI behavior, but I won't have too much time to get into that. I'll focus on the first two aspects that I'm showing here, and I'm happy to take questions or discussions about the last application. So in this, I'm going to focus on well-founded state and action abstractions, by which I mean I'm mostly interested in abstractions or mechanisms that allow us to provide strong guarantees of correctness. So let me start with the usability aspect of data efficient planning and learning. Now, abstractions on their own are not a new idea in AI by any means. In fact, from the earliest developments of planning, people started thinking about how to do abstraction or use abstraction to reduce the effective planning horizon. For instance, if you want your robot to do the laundry, the natural decision cycle is at the level of milliseconds. And in that decision epoch, if you count, there'll be millions of cycles before you actually have the robot loading everything into the washer. And that's a very low level of detail. It's not scalable. So immediately people started thinking about abstraction in terms of actions. So for instance, can I think instead of picking up objects, placing them somewhere, moving the robot from near the table to near the washer, things like that. And that for the large, for most part, that works well. So that's one very strong reason why abstraction is already there and in use in AI planning systems. Another reason why people use abstractions a lot is because users often think of goals and preferences at a very abstract level, and we need to be able to reason about them. And finally, as I mentioned, it turns out these abstractions also help in these newer problems of interpreting AI behavior, explaining it, as well as figuring out what their limits of functionality are. So I'm going to be talking about abstraction. So just to give you an intuitive idea of what I mean by abstraction, here's a situation where, to start with, I'm not using abstraction. So it's a concrete state description, and it's giving you the locations of different items of clothing and the exact joint values for each joint in the robot assembly. Right? And it's giving a concrete goal. So it's giving specific locations, and hopefully all these locations are in the washer. So it's, it's specifying a problem situation where initially things are wherever they are, and eventually we want these particular items to be in the washer. Now, this is good in the sense that this level of detail helps us express dynamics accurately. So in this particular state, if I consider what's going to happen if the robot moves its arm forward in this particular way, I can tell what exactly is going to happen, and I can plan accurately. But the problem is that this requires goal specifications at a very low level, and it's not always easy to do that for users. Of course, the other limitation of this resulting in very long planning horizons that continues. So this is not very scalable. By abstraction, I mean state aggregation as a starting point. So here now I'm saying the location of short one is a table. So that's like a conglomerate object representing multiple possible locations that I'm denoting as a table. And I can express my abstract states using these kind of logic-based properties. And I can also express an abstract goal much more conveniently. The downside with this abstraction is now dynamics become difficult to express. Using the amount of detail I have on the right here, it's not easy for me to say what exactly is going to happen. if the robot moves a certain way because I can't predict what the collisions would be. And it turns out that despite this limitation, this imprecision that is caused by abstraction, you can actually develop efficient task and motion planning algorithms that incrementally collect detail from the lower level concrete description and add them to the higher level model and keep refining this as needed. And we developed a bunch of task and motion planning systems using this. So all of these experiments are with one system actually. But what this system allowed us to do is pair arbitrary high-level planners with low-level planners. And it was doing this by keeping track of which parts are abstracted. And whenever there was a conflict in high-level and low-level, it would refine that. And this idea works quite well. So on the right, you're seeing a task that is quite complicated for a robot. Let me see if I can turn my pointer on here. Yeah, so on the right here, we have a task where the robot has to, now it doesn't work. So yeah, so on the right here, we have a task where the robot has to pick up the red object. And it's a difficult task because it can only grasp objects from the side. So it has to figure out where to place them. On the left, it has to set the dinner table. And we used an optimal high-level planner here. So it was able to figure out that using a tray is good because you can move multiple objects at a time. And then it used a low-level planner to figure out which hand to use for each placement. And on top, we have a generalized planner that was able to figure out, hey, regardless of the number of clothes, here's this iterative plan that you need to execute in order to get all the clothes into the washer. So this was a pretty, robust set of experiments, assuming full observability and only limited forms of uncertainty in movement. So what we really wanted to do was take this as a starting point and address the question of what happens if the robot's movements or mechanisms and these high-level actions are stochastic. And that opens a whole other can of worms. For instance, even if you were just picking up a bunch of cans and placing them, and you have some uncertainty about whether or not your pickup action is succeeding, you get this exponentially growing tree in terms of the horizon. So the numbers here represent probabilities of different outcomes. And the numbers at the bottom here represent the total probability of a particular path. Right. So what we wanted to do was solve these kind of situations or come up with policies for solving stochastic versions of task and motion planning problems. And this is difficult because of this exponential growth problem. So what most task and motion planners do in these settings is one of two things: either compute the whole policy, which can take a really long time, and so it turned out to be impractical for most real world situations, or take the most likely action or the most likely outcome of each action and plan for just that most likely sequence of outcomes. And these are both extremes, of course, so we wanted to see if there's a middle path here. And what we thought we could do instead of either completing the full policy or just taking the most likely outcome is to view this as a meta-level knapsack problem. So each execution outcome sequence here represents a particular real-world situation, right? And its probability is so much over here. And you can view this as the value of refining this particular path into a bunch of motion plans for the robot. So each node here is representing a high-level action. So a pickup can action is actually a set of low-level planning problems for the robot because it has to figure out how to pick up the can, what grasping pose to use, how to move to it, and how to raise it. So you can view two things about each path here. One is the value of that path, as in what is the probability that I'm actually going to encounter this sequence of outcomes, and the other is the cost. How difficult is it going to be for me to compute a plan for this? Now you can formulate this as a knapsack problem at the meta level. You have a fixed computational budget, and you somehow want to get the most bang for your computational buck. And knapsack problems are not great because they're also NP hard, so we don't want to solve that directly exactly. But what we found is if you can make an approximation, a greedy algorithm works out quite well. And under idealized settings, it also lets us prove some bounds on what is the amount of probability mass that is uncovered by a particular execution. Um, so this turns out to work quite well. And to illustrate that, I have a bunch of plots here. So what we're seeing on the x-axis is the time taken by our solver. And each plot here is a different domain, a different problem. And on the y-axis, we have the probability mass refined by the solver. So you can see the blue line, which represents our stuff, is quickly resolving or computing plans for a pretty high likelihood of possible outcomes. And the dotted line is what happens if you randomly pick paths from that contingent tree and compute motion plans for it. So this is nice because it gives you a middle path or a knob in the sense that based on your risk tolerance for your domain of interest, you can choose when to start execution. Maybe you are okay with 60% probability mass covered. And that means you can start execution within about 250 seconds, right? If you're really serious about a domain and you want like 10 to the minus 9, then you want to wait longer, but it gives you more control on starting your execution, and it makes things more practical. So we tested this algorithm with a bunch of domains, and I really like these particular examples here because what's happening is the robot has to build a structure using Kiva planks. Kiva planks are notoriously unstable, but the uncertainty here is that the human is going to place planks in one of two different locations. So if you have n planks for each pickup, the robot has to plan for two possible outcomes of where the planks is placed initially. And our anytime planning system works quite well for this. My favorite example, of course, is the one on top, which is the 3-pi structure. And it's really hard to build. I can build it sometimes, but I have to be very careful. So it's great to see that the robot is able to do that. So any questions so far? All right, I'll carry on. So what we saw so far is that if somebody tells me what these high-level actions are, like pick up and place, and what the probabilities of the outcomes are, and so on, we can do quite a lot. We can plan with real robots, and these are pretty long horizon problems, so things are working well. Now, the Achilles heel of this stuff, of course, is where did these abstractions come from? How did we know that pickup action is good and how it's described and so on? And usually these abstractions come from domain designers, and that has pros and cons. So you have a human who's designing this domain, and if that human is really an expert and know what kind of tasks the robot has to solve, the abstractions can be very good. And of course, a side effect of this is that if something goes wrong, you just blame the domain designer. It's not your algorithmic fault. So in some sense, there are some advantages there. But the problem is that because this is hand-coded and intuition-driven, it often leads to incorrect abstractions. You can end up in situations that are not Markovian even. So there is some benefit or value in being able to learn these abstractions. And the question is, how do we do that? In particular, how do we learn high-level actions? So if you think about it, a high-level action, even a pickup action, is moving between state or regions in the state space that are important. For instance, having the gripper empty versus having something in the gripper. This is a good action. I call it pickup because having something in my hand is generally useful. It's a critical region. If you think about this hallway, what's happening is if I want to go from the blue square to the green square, and I want to give somebody instructions, what I would do is say, hey, go to the corridor, cross the corridor, and get to the other side. So this high-level action that I'm thinking of can be thought of as simply a transition from a critical region of the state space to another. So if we can learn to predict these critical regions, we can actually learn to discover high-level actions automatically. So with this in mind, we define this concept of critical regions more precisely. And what this is doing is basically defining the solution density. So imagine that you have this rectangular robot. So describe a configuration for the robot or a state, you have to tell me X, Y, as well as theta, because it's not symmetric. Right? So I have this robot and it needs to get to the other side. I generate a bunch of problems in this particular environment. And produce solutions for all of them. This is a small environment. You can actually use existing motion planners to compute solutions. And you plot the solution density as a histogram. So this plot is basically showing how likely a particular point was to be used in a solution from this input problem distribution. So we get something like this. And the idea is to be able to learn to predict that these areas are critical. So armed with this definition for critical regions, what we did was generate a bunch of training data for small environments. So here we're seeing some training data for the rectangular robot. One thing to keep in mind is that these are high dimensional robots in the sense that even though that's like looks like a 2D image, you've got to specify X, Y, and theta. So you have to provide critical regions for each of those dimensions. So this data is quite interesting actually. So what the plot over here is showing is what is useful for the base location. And here we are getting critical regions or histograms for the angle for the base. That's the rotation. So here you can see in our training data, it's very likely that at these points, the robot was oriented vertically. And similarly, you can increase the dimensionality of the robot. So here we have an additional dimension, which is the hinge angle. And you can produce critical regions for the hinged angle similarly. And you see that this is reflecting quite what you'd expect. Over here, the hinge angle is 180, as you'd expect. So it has to be straight when it's over here, and it becomes again a bit angle at this point, so 90 degrees at this point. So there are no surprises here. This is just training data. We generated a bunch of problems using this robot for this simple environment, computed solutions, and plotted what is the more likely joint value for each joint. So that's our training data. And we created a deep neural network to predict this kind of critical region. Right? So here are some results from the predictions. And you can see it's getting quite a lot of interesting details. So for instance, this is for the rectangular robot, and you can see it's predicting that over here, the robot should be vertically oriented, which makes sense. Over here, it's saying, hey, your robot should be straight here, there should be an angle. So it's sort of getting things. There are obviously mistakes here. For some reason, it thinks it should be at an angle at this point over here, which is not really needed. So it is making mistakes, but it's fine. It turns out even this kind of prediction is useful. So when we saw these results, the first thing we thought of doing was to say that we have sampling-based motion planners already. What we're going to do is take points from these critical regions and tell the motion planner to try to get to them. And unfortunately, that doesn't work, because when it tries to connect go from a point here, for instance, to a point here, it just crashes into the wall. So that doesn't work very well. So what we thought was, okay, we need to give it a little bit of a look ahead. So what we should be doing really is to discover high-level paths and then try to refine them. Or in other words, we should be doing some hierarchical search. So in order to do that, what we did was took the high-dimensional critical regions, and I can't show them very well on these slides, so I'm showing them separately here. And then from each critical region, we grew these Voronoi cells, which we are going to interpret as high-level states. And again, I'm showing a projection of these cells in a very large environment here. Okay. And once we have these abstract states, we formulate high-level actions as moves between these abstract states, right? But again, we can't do vanilla hierarchical search because we don't even know what the neighbors are. All these abstract states are generated automatically. And computing neighborhood relationships is just going to break efficiency. So what we did instead is, once we conceptualize these abstract states, we don't actually generate all of them. We conceptualize a bidirectional multi-source search. That is, we're going to start our search from multiple points in this abstract state space and try to connect them to the start and goal. And that's an interesting idea. It works here because we're getting these critical region predictions. It normally doesn't work because it's very hard to predict what states are going to be close to a path from your start to the goal. But here we're getting these predictions, so we can do that. So the overall algorithm is follows. We in the beginning, we generate this training data and we train our network with a particular robot using very small environments. And that's just the algorithmic design phase. Okay. Now, when we get a new environment, for instance, this one, what we do is predict the critical regions and carry out this high-level search. And in particular, it's going to be a multi-source bidirectional search. Now, one thing to keep in mind is that there's a lot of generalization happening here. So this environment, for instance, is 25 meters by 25 meters. It wasn't in the training data. In fact, all training data environments were 5 meters by 5 meters. So what we're doing is using the sliding window method to predict critical regions for these entire environments. And this method overall works quite well. So this is a bunch of training of test environments that were not seen in training. And we went ahead and computed how our method performs on these environments. So here are a bunch of results. We experimented with a whole range of robots. So R is a rectangular robot, H is the hinged robot. Car robot has the car-like dynamics, so it's a bit like a Dubin's model. You can only control the velocity and steering angle. And then you have the fetch robot, which is a manipulation robot. So there are different types of environments here, and none of these were in the test data. So what's happening in these plots is x-axis is showing you the time in seconds, right? So this is the time limit actually that was given to the planner. And the y-axis is showing the percentage of problems that the planner could solve within that time limit. The blue lines are the planning approach that I just told you about. And what's interesting is that you can see clearly it's doing much better than existing baselines. And some of these baselines don't use learning. But the interesting thing is this orange one is our own previous work. It uses the same critical regions. So it's using the result of learning. And it's still not as good. In fact, it's much poorer than the version of our approach that uses critical regions and also builds abstractions. So this was a bit of a surprising result for us, but the performance is clear, advantage is clear, and it exists over a huge range of environments. We've been testing it ever since we saw this. We've added more environments that we hadn't even thought about at that time, and still works. So this was a very surprising and nice result for us. And these results are going to be presented in a few months at AMOS. So the moral of the story here is that discovering and using abstractions does improve performance. It makes things much more data efficient. And in fact, by designing this algorithmic process around the noisy predictor, we're able to do much better than an approach that does pure learning or approaches that don't use learning at all. And of course, there are many more results in the paper. So I want to pause here and see if there are any questions.
So I have a question. I mean, you probably explained this, but when you come up with these critical regions, you see they're coming from training data, but does it mean like you've observed another robot solve this task? Or because there's a chicken and egg problem, right? To find the critical regions, you have to kind of get a distribution on the plans, but to find the plans, you have to find the critical regions. And so, yeah, I'm wondering how that works.
Yeah, good question. So for any robot, so the way this works is you give me a robot and I generate training data for that robot on small environments where my existing planners that don't use learning are actually able to solve the problem. Okay. So the training for these robots was on environments of this size, 5 meters by 5 meters, like A and B are of the same dimensions as training data, but they were not in the training set. Okay, now once I learn to predict critical regions in that dimension, when I get a huge map or a new map, I just take that map, the occupancy grid as in where you have collisions and where you don't, and I predict critical regions for portions of that map and then stitch them together.
And so the neural network is somehow applied to these new layouts in a way that, kind of generalizes across them. Okay.
Exactly. Exactly.
Okay, thanks.
Exactly. Yeah. Any other questions? All right, great. What we saw here is that using these critical regions or the neural network and its noisy predictions with the algorithmic process that we designed is actually quite powerful. And we have pretty good formal results here. So these methods are probabilistically complete. So they offer the same guarantees of completeness and correctness that you get with purely analytical methods or algorithmic methods. And for some robots that are omnidirectional, we can actually go stronger in the sense that we can say downward refinability is going to hold. That is, you only need to compute the higher level plan and go down once. There's no need for backtrack. So all of that stuff in the paper, but I'm happy to take more questions on that. So what we are seeing here is that the overall process was as follows. We saw some executions, that was our training data. And based on that, what we effectively did was create an abstraction generator. And what this thing does is effectively reduces planning horizon. So when you get a new problem, we're going to use that, we use that abstraction generator to reduce the horizon and then did this hierarchical planning, which turned out to be really, really efficient. Now, it turns out that if you can readily create state abstraction so that you don't need this piece of the puzzle, you somehow get it, you can do even better. And we can do this, for instance, in symbolic planning problems, where you express a state using a relational model, for instance. And in this case, what you can do is get a small set of observed solutions, so in the hundreds, not thousands, and then use one of the logic-based abstraction techniques to generalize that training data. And then what you can do is learn a distance estimator between these symbolic states, and then use that as a heuristic generator so that when you get a new large problem, you just use that heuristic and use search to solve it. It turns out this method also works very well. And I'm not going to have too much time to get into it, but because this works well, what we did was took this a little further and said, suppose you have no training data at all, but you have a problem generator with you. Then what you can do is start with a zero training set and start with a basic blind search algorithm and generate small problem instances at first, use that to start generating data for your relational distance estimator or heuristic generator, and then bootstrap this entire process by getting larger and larger problems. And this turns out to work very well. It is able to find plans with zero training data to start with. It's not exactly perpetual motion, so just so that you know I'm not pulling wool over your eyes, there is a problem generator here, so I'm getting some new information. And the interesting thing is, because it's a symbolic domain, I'm able to generate this heuristic. And additional plus point of this is that you can do this without even looking at logic-based action descriptions. So you don't need to express your dynamics in logic, you just need to express its states using relations. This works very well. We shared some results about this in last year's AAAI, and I'm happy to take more questions about it at the end, although I want to move on right now onto the next part of my talk. Before I move on though, this is a good time for questions if anyone's been saving them up. All right. So now what I want to talk about is the learnability aspect. That is, how do we enable users to assess what the AI systems can and can't do? And there are two major challenges in this direction. One is that things change. So requirements change as well as deployments. So for instance, if I have a self-driving car and I was able to get it to back itself out from my garage today, suppose it goes through a software update or learns something new and gets a result of that. How do I know whether it's still going to be able to do that after this update? How do I know it's still going to be able to back out of my garage? So that's an example where the system changed. And humans have this long history of being innovative with the way we use things. Right? So, for instance, those robot vacuum cleaner designers had no idea that their system could be used as a robot, as a rodent transportation platform. So they have to deal with that, right? So how do we create a situation where a user is able to understand the limits and capabilities of their system? And also, if that system changes, how do we help them to understand what are the differences? What changed? Can we do that efficiently, or do we need to reassess the whole thing from scratch and send it back to the manufacturers because, hey, I changed this little part in my deployment scenario, or because you changed this part of your software, now here's my map of the home and test it again for my entire plan. Can we avoid this entire thing and do a differential assessment? That's one challenge. The second challenge is AI in general, AI systems of the kind we are talking about, go far beyond their primitive actions or primitive functionality. We want to assess what their capability is rather than functionality. And to clarify what I mean by these two terms, by functionality, I'm thinking of simply the set of possible actions that the AI system could do. These are its choices. For instance, in this game environment here, you have this character called Link that the AI system controls. And this guy can basically move up, down, left, right. It can interact with the environment. So its basic functionality is just this set of actions. But telling a user that, hey, your car can move forwards and backwards at different speeds doesn't really tell the user what it is capable of doing at a higher level. So what we want to find out instead is, in a scenario like this, can this AI agent do things that matter to it? For instance, can it go and pick up the key? Can it open the door? Can it defeat the monster? So the question here, this challenge, is about figuring out what are the relevant capabilities that the AI system has learned. So high-level capabilities, can we discover them based on the agent's behavior? So these two challenges, and we as humans regularly solve these challenges. For instance, if you have a person you're interviewing for a new job, you might go through a query response phase, as in you ask them some questions. Based on their responses, you figure out, well, have they learned something new? This is what we try to do in our exams. Or what do they know about? What are their capabilities? And we do this implicit extrapolation based on their responses. But when you replace the person or this job candidate with an AI system, things become very difficult. Because now, especially if the user is not an AI expert, it's not clear which questions they should ask. And it's also not clear how they should extrapolate from the AI system's responses to what it can do in other general situations. So what we need in this kind of a situation is a well-designed AI that can talk on behalf of the user to the AI system. And this is very much like what we see in automobiles today. So you have something called the onboard diagnostics tool. And this is a system that can plug into your car and quickly give you a summary of what's going on with the car. It's exploiting an external interface or an external query protocol, which doesn't depend on the internals of how this car is designed. It just works with different manufacturers. So the question is, can we design something like this for AI systems? And in particular, we want to design it in a way that's non-intrusive so that the internal design of the AI system is not constrained by whatever requirements or need to hold for this thing to work. So this was the question that we were working on. And what we found is that if you can impose a query response protocol on an agent, so for instance, the agent should be able to accept two kinds of queries. One query is, can you execute this particular sequence of actions starting from a given state? Okay, and the response would be something like, I can execute so many steps and I end up stopping here. And this, we only want the AI system to be able to do in a simulator that we have. The next kind of query is, can you go from state SI to state SJ? And the response is a simple yes, no. Right. So this is the very limited class of queries that we are working with. And this is actually a fairly reasonable categorization of query and response protocols. Because it turns out that any practical AI system that you develop has to be able to take instructions. So it has to reveal its instruction set. So we get to ask these kind of queries. That's not placing too much of a requirement. And in addition, most AI systems that we deploy are actually tested with simulators. So they already have the simulator hookups. So we're not asking for too much here. The big question, of course, is how do we generate these queries and how do we learn from those responses? So this is what our research addresses. And just to overview, the overall setup is as follows. You have this black box AI system, and the user doesn't understand what its capabilities are. And in fact, most of the time, it's not even clear what this thing is saying. Right? So there's this black box AI. And what we want to do, of course, is generate its buddy here. And this guy is going to talk to the robot, the black box AI, on behalf of the user using that limited query response protocol, and eventually get back to the user with an interpretable model of the black box system's capabilities. Okay? So we are assuming that this guy in the middle over here, the personalized AI evaluator, does get some information about the user. And in our experiments, we just assume that basic English semantics hold. So for instance, we know that the user understands things like the object X is in the gripper of the robot and things like that. So that's the overall setup. Any questions on stuff so far? Okay, so that's our setup. And what we're going to do is use these kind of models to explain the robot's capabilities or to express the robot's capabilities. And many of you might be familiar with them. They're simply saying if these preconditions hold, then the robot can execute the pickup action and it results in this stuff. Right. So these are very nice. They're desirable. They're easy to interpret. They also allow assessments of causality. So these are very nice representations for the model of an AI system. The only catch is that there are too many such models. In fact, if you have p predicates and it's 9 to the p, so it's exponential in the number of relations you want to use to express things. So we have to be clever about identifying the right model of the given AI system. And in order to do that, we found that abstraction is really helpful once again. So what we did was started with this conceptual abstract node consisting of an empty model. And I'm thinking of that empty model as the most abstract possible model. And each edge here going down is like an edge in a lattice of refinements, or going upwards, it's abstraction. And suppose you have this one predicate hand empty, and we don't know whether or not it's the precondition of an action or it's in the precondition of an action. We can partition the space of all possible models by different forms in which this literal could appear in the precondition. Right? So that gives you large classes of possible models. And here's the interesting part. Once you do this, we can take any pair of these abstract models and automatically generate a query that distinguishes between them. So a query is a sequence of actions here. And I'm saying that we can automatically generate a sequence of actions such that the result of those actions on MA is not equal to MB. So we can take pairs and generate these queries automatically. And then what we do is give that query to the real agent. Right? Remember the query response protocol, I get its response. And if the response is not consistent with MA, I throw out MA as the set of possible models. And if it's not consistent with MB, I throw out that entire set. So this quickly prunes away large classes of models, and I keep repeating this until I discover a fit model. And this method works very well. The closest comparison to this kind of an approach is with passive model learners, which just observe the behavior of an agent and try to derive a model of functionality, like using the same kind of a model representation. And it turns out our approach does much better. So in this plot, on the x-axis, we have the number of queries asked. And on the y-axis, I'm showing two plots. On the left, we have model accuracy. So this is showing, did I recover the full model? And our approach, the solid blue line, always gets there. So it always converges to the true model. Actually, we have a theorem, it will do that. So it wasn't very surprising, but this gives you an idea of how long it takes to do that. And the dotted lines are representing the time taken per query. The orange line is the passive learning baseline. And you can see sometimes it doesn't converge to the true model. And this is because it's a passive learner. It's not making any interventions. So the models that it learns are actually not causally accurate. They're not guaranteed to be causally accurate. And so there is only so much it can do. So this was all about functionality. So all of these stuff was learning about agents functionality, right? So just a little bit further on this, and then I want to switch to capability as my concluding section of the talk. So we can discover functionality this way. And remember, one of the challenges I mentioned was if something changes in the agent, can I do a differential assessment rather than assessment from scratch? So if there are agent update events, I get a small data set of observations from this new agent, can I find out, and can I raise queries more intelligently so that I do only a differential assessment? It turns out this is true. This work was presented just a few weeks ago at AAAI. And in these plots, what we're saying on the x-axis is the percentage of drift. So that's how much the agent has changed. At 1, the agent has nothing to do with the previous version of the agent that we saw. And the blue lines here are showing the number of queries we have to ask. And the purple area is showing how much accuracy we recovered at each query point. This X over here on the Y-axis, this represents the number of queries that we have taken to reassess the model entirely from scratch. So you can see that with a small fraction of the queries compared to the total number of queries that we have needed, we can cover quite a lot of the agent's model quite accurately. And of course, at a certain point, when you have more than 50% of so drift, it might make sense to do the assessment from scratch again. But at least if you have small incremental changes, then on a running basis, you can do this sort of assessment accurately. So this looks at the first challenge that I mentioned. That is, if the agent changes, can I reassess efficiently? Now I want to get back to the second challenge, which was, can I discover the high-level capabilities of what this agent can and can't do in terms that the user can understand? So let me go back to that example where we have this small game playing agent. Okay. And now what I'm going to do is use abstraction as a sort of filter to prune away irrelevant detail from the point of view of the user. So I'm going to let the agent run. And as it's going about doing its business, I'm going to give it a bunch of random goals. And as it goes about and moves in the environment or changes things in the environment, I'm going to view the state through the lens of terms that the user understands. So this abstract state, for instance, corresponding to terms that the user understands, is simply saying the player and the monster are in neighboring cells. And as the agent goes about, it does things, all of these states actually have the same abstraction. So I say, from the user's point of view, nothing much has changed. Now, the moment something changes, that is, I get a state that is falling in a different abstract state, I consider this as a cue to flag a potential capability or a high-level capability of the agent. So here I'm saying this is a candidate capability C1, something changed at the abstract level, and maybe we should find out more about this. So we keep doing this and collect these candidate capabilities. And so far, all I know about these is that there are some transitions in the abstract state space that this agent has the capability of making. I still don't know when exactly it can make these transitions, right? But this is where all the hard work that we put in query response protocols comes in, because now I can query the agent about this particular capability and learn exactly what it needs in order to be able to execute that capability. And this works out very well. So for instance, in this example, we got some agent behavior that was going from this start state to this end state. And I should mention that all of these are actual pixel states in our problem definition. So these are pixels, and we have classifiers that tell you the truth value for each predicate in the user's vocabulary for any input state in terms of pixels, right? So we have the start, we have this end, and our algorithm is just getting that as data from the agent. So even the state annotations in terms of relations and predicates has to be done through a classifier. And this is the kind of stuff that our algorithm ends up discovering. So here it is saying if these preconditions hold, then this is going to occur if the agent executes this capability. And you can easily transcribe this into plain old English. And if you spend some time on it, it's basically discovered the capability of killing the monster. And all of this was done automatically based on the queries that we raised. It turns out this method can be done for a range of domains. So these are all game playing domains from a game playing AI suite of benchmarks. And we tried it with different types of agents. So agents that at their lower level use search to find out what to do, or agents that have black box policies that could be hand coded or learned. And it works quite well. It's able to discover capabilities, but it doesn't still tell us whether or not those capabilities are useful. So we conducted a user study, and in this user study, we gave the users a sequence of primitive actions or capabilities and asked them whether the agent can go from one state to another if it executed this string of capabilities or primitive actions. And then we computed, or we evaluated the users based on the time it took to answer them. So these orange boxes here show you the distribution or the dispersion over how much time it took. And you can see it's uniformly a little lower than the amount of time it took for users to answer questions using primitive functionalities. So that is good. And these boxes and triangles here are representing how accurate the responses were. So you can see that using capabilities, users were uniformly able to answer queries about these kind of what the agent can and can't do kind of queries more efficiently using the capabilities that we discovered. And one interesting thing here is we didn't have to train the agents on this vocabulary or anything. We just assumed normal English. That works fine. So I want to stop here. I hope I've given you enough examples and snippets of research and results to convince you that abstraction can be a powerful technique for developing P2 kind of systems. I didn't quite get enough time to get into some related results on planning and learning and computing explanations and planning around humans. So, feel free to check them out or ask me questions. I'm always happy to discuss. Currently, we're using the stuff that I showed you as, really building blocks and developing more general methods for stochastic environments. Our source code is available with published papers, and you should be able to access it freely if you want to try any of this stuff. And do send me a note if for some reason you're not able to access them. And this was joint work with a fabulous team of collaborators and students. So I'll stop here. Thank you.
Thank you. We have time for questions. I guess folks can just raise their hand, and I guess we'll see that happen. In the meantime, maybe a naive question, but so the description, the symbolic description of the abstract problem or the preconditions, you're not just learning these symbols completely from scratch, right? You do have some vocabulary available.
Yes, that's right. So the setup is where we get a bunch of information about the vocabulary and semantics of the user, right? And this is our starting point. Now, that said, these studies were done on Amazon Turk. So we didn't actually get this, right? We just assume people know English.
Oh, but for the earlier part where you, okay, so you're, I see. So there's never going to be any issue with when you learn the symbols that, what is holding and what is the gripper and any of that. It always is routed through the human understanding. There's no
right. exactly. So if, for instance, I got somebody who didn't quite speak English, I would have to, get their terminology and their semantics somehow, or I could use a dictionary. That might be easier, and get this initial information about what it means to the user to say holding. And what I could do is, say that that means that if it's holding X, then X should be within this area of the gripper and things like that. I can define those things or even train classifiers. But in these experiments, we didn't do any of that. They were all standard interpretations in English.
And then another kind of more open-ended question perhaps is, so I'm trying to think, where in AI can these kind of hybrid symbolic and perception type of models really play a role? And, there's a lot of folks now doing neurosymbolic learning. And I would argue one of the key problems there is also to discover what are the actions, what was the symbolic abstraction of the domain.
Yeah.
I mean, you have essentially already solved that problem as like a subproblem of this this work.
So I think a closer aspect for that is this stuff earlier that I mentioned about the hierarchical action discovery in time, where we are automatically discovering abstract states and then defining actions as moves between these abstract states. Now, this is all early work in some sense, because so far the abstractions that we're learning here is not directly interpretable. I can't even show it to you because they're high-dimensional abstractions. But eventually we could actually use methods, some of the methods from the latter part of the talk about interpretability, and start making sense of this for humans.
But even with these abstractions, it seems like they would be useful kind of in neurosymbolic learning, even though you don't really know what they mean and they don't have an English name, but you could learn a symbolic.
Absolutely. In some sense, that is what we're doing. The term neurosymbolic, I find a bit ill-defined. It is trying to do a lot of stuff that people were trying to do even before the neural network thing became extremely popular. The sense of learning from data and then discovering symbols to describe that. So we are doing that. We get these discrete areas. You could easily call each of these S1, S2, S3 and give them some names if you really want to make it explicit in the sense of symbol discovery. But the interesting thing is it's not just for aesthetics here. It actually helps us plan faster. So there's something to say about humans using, these symbolic ideas to plan and reason with.
Yeah, but I think the same argument could hold for just classification, where if you're able to infer some symbols, then it becomes easier to do a good job at classifying images, right? So I think
you mean like clustering before classification?
Yeah. So essentially places where currently people say, oh, we're going to say what the symbols are and say what the constraints are on my outputs of my predictions, you could essentially bootstrap the whole thing like you did here. So I feel like your technique here has more kind of wider applicability in other areas of AI beyond planning. Yeah.
That's cool. That's cool. Yeah, we should talk more.
Okay. Any questions otherwise? The audience is very shy today, or somehow they cannot raise their hand and we don't know about it. Not sure which is the case. But if there's no questions, then yeah, let me thank you again. A very interesting talk, and thanks everyone for attending.
Great. Thank you all, and thanks, Steve, for hosting. It was a pleasure to be around.
Bye-bye.
Bye.